Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Today I'm going to tell you about a story of trying to understand the dynamics and the nature of natural gas bursts. These are hazards that we didn't know about 20 years ago, 25 years ago, and I've been working on them to try to understand how they operate and what we can actually do about them. The study of these phenomenon, these lethal gas bursts, have required lots of help, lots of different funding agencies, and I want to especially, I think I can try to show with a pointer here, highlight the U.S. Office of Foreign Disaster Assistance has provided most of the money for this work that we've done over the years, and also many different governments. It's been a true international effort. And of course, it wouldn't have been possible without the help of very many people, especially here Greg Tanyilike, our Cameroonian colleague, Minoru Kusakabe, our Japanese colleague, and especially Bill Evans, whose scientific insight and common sense has been really great for the project over all these years. And of course, as with all arts and sciences, if one person is standing up at the podium, it means that several other qualified people are taking a back seat. So I want to thank them. Most lakes, outside of the occasional boating accident or drowning, aren't found in the news outside of the fishing reports. But when lakes rear up and kill thousands of people, they actually make news. And so what is special about these lakes? There are only 3 lakes in the world that are known to have high concentrations, lethal concentrations of dissolved gas in their bottom waters. Lakes Nyos and Methane in West Africa, Cameroon, and Lake Kivu in East Africa. In 1984, Lake Methane, so this is Lake Nyos here, much larger Lake Kivu, a rift lake in East Africa. In 1984, Lake Methane, a smaller lake about 90 kilometers to the south of Nyos, released gas that killed about 37 people. And in 1986, Lake Nyos released enough CO2 to asphyxiate about 1,800 people. Since that time, the gas has been recharging into those lakes, and the continued threats have kept about 5,000 people away from their homes as refugees for almost a generation now. There's a tremendous amount of steam which then rips up through the surrounding bedrock, the country rock, and you can see that from these, you can see the country rock here in these cliffs along the edge of the lake. There we go. The lake is, we're looking here at the spillway, the natural dam holding back the upper part of the lake. The lake extends from here back to the inlet about 1 kilometer. It's a fairly small lake. It's about 1 kilometer wide, but it's a very deep lake, about 210 meters maximum depth. Then about 10 days after the disaster, the gas burst in 1986, the lake looked like this. The most noticeable change, of course, is in the surface color of the lake. You can see mats of floating vegetation, but it's important to notice that around the lake there's no evidence that any of the vegetation had been burned. When the sun was out, it really highlighted the color of the lake. And this was not due to sediment which was thrown up from the bottom waters, as was initially thought. It's actually due to an iron hydroxide flock that's formed when dissolved iron deep in the lake is brought up to the surface and contacts oxygen. It forms this iron hydroxide. It's essentially like rust on the car. If you chip the paint on the car, the metal will rust when it's exposed to oxygen. Below about 10 meters, there was no oxygen, and from there down to the bottom of the lake, the water was perfectly clear. This is an aerial view of Lake Nyos. The first picture was taken standing on the rim here, looking down to the spillway. So this is the entire lake. We estimate that up to 1 cubic kilometer of CO2 was released from Lake Nyos. And to give you some sense of perspective, most of you probably remember the Mount St. Helens eruption in 1980. That eruption produced about 1/3 of a cubic kilometer of of ash. So a cubic kilometer of anything is a lot. It would fill, for some local perspective, it would fill our Big House Stadium about 125 times over. So there's a tremendous amount of gas released. The focal point of the gas release appeared to be somewhere here in this area of the lake. It produced a gas water fountain which went up over this 80-meter high rock promontory here with enough force to wash away all of the vegetation and soil down to the bare bedrock. It also produced a 25-meter high surface wave that washed up along this edge of this end of the lake all through here. You can see all of the vegetation through here was just trashed by this wave. Again, for some local perspective, for those of you walking around on campus, that 80-meter high gas water fountain would have topped over the U of M clock tower, and the 25-meter high surface wave would have topped Hill Auditorium. So next time you're out there, look at those and think of the wall of water coming there. The gas came out of the lake and filled the basin up to about 100 meters height above the lake surface. And we know that because above 100 meters in the crater, there were no dead cattle, and below 100 meters, there were cattle everywhere. Because the CO2 is about twice as heavy as air, it was more dense and flowed out over the spillway and down through the river valleys, where it killed almost 1,800 people. There were no witnesses to the event. It happened at night, but if there were witnesses, the event might have looked something like this. So this is the fountain that was produced. It doesn't have it washing over the lake, but the wave coming at you. The lake, initially, the gas came up fairly slowly to fill the crater basin, but then once it started moving out over the spillway, it was going very fast, 20 meters per second, about 45 miles an hour. So even if you saw the gas coming, you couldn't outrun it, and you couldn't escape it. Okay, if I can have the lights back up, thanks. In the end, the gas that was released from the lake here flowed out down over into the river valleys, where it killed people 26 kilometers away from, about 13 miles away from the lake. So a tremendous amount of gas. At this point, what I want to do before continuing the story is stop and do some review on the physical structure of lakes. And this applies to oceans as well. Most lakes are stratified. That is, they have less dense, warmer surface waters at the top here. And you can see over here a plot of temperature with depth. The warmer waters are up here in this surface layer. And that's separated from these more dense, colder waters in the bottom. And that separation here, where the rate of change of temperature is very rapid, is called a thermocline. It's the same thing we find in an ocean, a thermocline separating the upper layer from the bottom layer. The CO2 actually injected into water will make it more dense, as will salts. And as you increase the density difference between the bottom waters and the surface waters, you increase the stability of that stratification. The stronger the stratification, the less likely the surface waters are to mix with the bottom waters, and the more likely anything injected into the bottom waters of the lake will be retained there, will be kept in there because of the strength of this stratification. So, for example, if you inject CO2 into the bottom waters, it comes in as a dissolved form, and essentially the weight of the water on top of it is pressuring it, keeping it in dissolved form instead of coming out. So, in general, gases want to be gases. They want to be out in a gaseous form. They don't like to be compressed into water. They will dissolve into water, but it's sort of like stuffing a bunch of college students into a Volkswagen. You know, you can put more and more of them in there, but they're exerting a pressure out. And that gas is always exerting a pressure outward to try to get back into the gas phase. If the weight of the water or the hydrostatic pressure is greater on that gas than the pressure outward by the gas, then the gas will stay dissolved in solution. That's exactly what you see in a soda bottle or a beer bottle. You look at it, you don't see any bubbles. The cap is supplying the pressure which keeps the gas dissolved. If you release that pressure, then all of a sudden the bubbles don't have that pressure keeping them, the gas doesn't have the pressure keeping it dissolved, and bubbles form. So when we first got to Lake Nyos, we were worried that we were going out on a volcano. But we didn't really see any fresh lava flows or any fire fountaining. And what happened when we went out is we found that, in fact, the lake water was relatively cool. This is just a plot here showing the temperature across the top with the depth in the lake. And you can see that for both of these profiles, 2 different days, the water temperature is relatively similar from top to bottom. What that indicated to us is that there was a tremendous amount of mixing. The lake was no longer stratified. There was mixing during this event, and that the water temperatures were relatively cool, relatively normal. This increase up here at the very surface of the lake was due just to solar heating. Now, what do I mean by relatively cool? This is 23 degrees Celsius. For most of us, that's pretty warm. I mean relatively cool because when you compare that temperature to the bottom water temperatures of all of these tropical lakes, so we have here the bottom water temperature. Hypolimnion is just a fancy word for bottom. The lakes that are lower in lost my pointer. The lakes that are lower in elevation here have warmer bottom waters. And as you increase elevation or altitude, you have colder bottom waters. That makes sense. You get higher up in the mountains, the lakes are colder. But the important thing here is to look at the point for Lake Nyos and Lake Manoon right there. Both of them fall right on this line describing these 43 tropical lakes that haven't had any kind of a gas burst. What we inferred from that was that there was no major input of heat into the bottom of these lakes, and that there was no major body of magma very close to the surface that was heating the bottom waters. There was really no volcanic activity associated at all with these events. So, where did the gas come from? Well, initially, many people, the volcanologists especially, thought that this was just a volcanic eruption and the poor little lake happened to get in the way. And at first there was some anecdotal and circumstantial evidence for this because most of the survivors reported smelling gunpowder or rotten eggs, which are unmistakable smells of sulfur gases, and they reported feeling very warm. Well, we know volcanoes produce a tremendous amount of heat, and we know volcanoes produce a tremendous amount of sulfur, and so that made sense, that fit very well with the idea that this was a volcanic eruption. However, when we went out on the lake, we looked in the water, there was no sulfur in the water in the lake. There was no sulfur gas dissolved in the lake. There was no sulfur, excess sulfur in the plants around the lake that had been exposed to the gas cloud, and they would have picked up that sulfur. And when the bodies were exhumed and autopsies performed on people who were killed, there was no excess sulfhemoglobin in their system. So that's a stable compound that forms with sulfur and hemoglobin that would have been there if they were poisoned with sulfur. So we had our first mystery. We had all of the reports of sulfur in the system, and we couldn't find sulfur anywhere. This was a problem for us because we didn't believe that this was a volcanic event. We thought that the water was stored, the gas was stored in the water in the bottom of the lake itself, rather than being injected through the lake in a volcanic event. And we had a problem explaining this until we ran across some older medical literature that had used high concentrations of CO2 to test for oxygen stress in fighter pilots. And it turns out that at concentrations above about 10%, CO2 acts as a sensory hallucinogen, so that you smell things and feel things that aren't really there. And the most common report from these pilots was that they smelled gunpowder and rotten eggs, and that they felt sweaty and warm. So that was the first way around this evidence that we had to explain away, that there was sulfur in the system. So where did the gas come from? Well, we ruled out a hot volcanic source. As I said, there was no heat in the system, no excess heat anywhere. There was no sediment that was thrown up into the bottom water from the lake bottom if the gas had been injected, even cold gas had been injected through the bottom. Remember, the lake water was very clear all the way to the bottom. And we never found any fissures or craters that would have been formed in the bottom sediments if there was such an injection. We also ruled out a biogenic source for the CO2 gas. And we did this because when we tested the gas in the lake, we found that its carbon-14 age was greater than 35,000 years old. And yet the lake itself is only about 500 years old. So there wouldn't have been enough time for bacteria decomposing organic matter to produce enough CO2 to account for what we found in the lake. And the age would have been very young, not very old, which is what we found. That left us with a magmatic source, and I'll get back to that in a second. We also ruled out the possibility that the gas was stored in fissures below the sediments, or that at least it was injected into the lake from below the lake. And that left us with the idea that the bottom waters themselves held the gas. If you fully saturate Lake Nyos with CO2, it could hold about 1.5 cubic kilometers, which is more than enough to account for the amount of gas that we estimate was released from the lake. So what do I mean then by a magmatic source? About 80 to 90 kilometers beneath the surface in this area of Cameroon. This is a volcanic region of Cameroon. Mount Cameroon's the only active volcano in West Africa. There lies a body of magma, and as that magma goes up and down, it releases gases. When it goes up just a little bit, the pressure, the weight of the rocks on top of it is reduced. The gases in the volcanic rock in the melt come out of solution, and they start moving up through the diatreme here, this fractured rock that was in place when the lake was actually formed. They get close to the surface and they meet groundwater. Now, on the way up through this rock, all of the reactive gases like sulfur, cyanide, and so forth are scrubbed out. And only the really unreactive gas, like CO2, is left. It meets the groundwater, and then that groundwater issues into the bottom of the lake in a CO2-charged, slightly warm soda spring. And what we found in the lake was that the gas that was dissolved there was about 99.6% CO2. So it was almost pure CO2. In fact, of medical quality, and people wanted to take it out to use it for that purpose. All right, that's a nice idea, but do we have any evidence for it? Well, in fact, there are many of these CO2-charged soda springs in Cameroon. Here's a picture of one of them. This is, here's Bill Evans, person for scale, sort of Bill's best side. This is not time-lapse photography here. This is just the CO2 coming out of the water, and you can see that the water is sort of iron-stained as well. Now, most of these springs simply discharge their CO2 harmlessly to the atmosphere. However, if one of these springs were to discharge into the bottom of a deep stratified lake, then you could have the kind of CO2 accumulation that we found. The real sealer of the evidence, though, on this idea was when we found that the bottom waters were chemically and isotopically similar to the spring waters close to the lake. So this is a plot showing the relative proportions of sodium and potassium, calcium over here, magnesium and iron over here. This is the relative composition of the springs close to Lake Nyos, and these are the samples for the bottom water after the event from Lake Nyos. The surface water after the event from Lake Nyos plotted here. And what you can see is that there's a perfect mixing line here between this bottom water, which we assume was there before the event, the pre-event surface water up here. So this water mixed with this water to form the surface water after the event. So this gave us an indication that the proximate source of the CO2 coming into this lake and probably the other lakes were these CO2 soda springs, CO2 charged soda springs issuing into the bottom of the lakes. Okay, so that's how we got the gas into the lake. Now the next question is, how do we get the gas out? There are actually a couple of ways that you can get the gas out of the lake. This is a plot showing the bottom 100 meters or so of Lake Nyos, and the total gas pressure here in bars. So a bar is just an atmosphere, 1 atmosphere at sea level. So we're up to here over 15 atmospheres of gas pressure at the bottom of the lake. Tremendous amount of gas. Oops. 1 liter of water from the bottom of Nyos, if you bring it up to the surface and let it degas, it produces 12 liters of gas. So there's a tremendous amount of pressure at the bottom, and that's what's keeping the gas dissolved. Now you could increase the gas concentrations here, this direction, until they hit this hydrostatic pressure line. This hydrostatic pressure line is just the weight of the water, a measure of the weight of the water on top of it. What's keeping the gas dissolved in the system? Once the gas pressure equals or exceeds the hydrostatic pressure, then bubbles will form, they will rise very quickly, and you will trigger a gas burst. The second way to get gas out of the lake is to actually take a parcel of water at this depth and move it upwards until you hit the hydrostatic pressure line. That is, have something that displaces the water, some disturbance of the water column that displaces the water upwards. You don't need to change the concentration. Now the gas is supersaturated at this new depth. And it's most likely that a landslide coming into the lake, into Lake Nyos, triggered the gas burst. And this is just sort of a representation of that. In fact, there was a huge landslide scar on the cliffs of Lake Nyos just after the event. Unfortunately, we don't know whether it was there before, but it was a very fresh scar. The rock comes into the water and starts to disrupt the layering and move deeper water up toward the surface. As the deeper water comes up toward the surface, the gas comes out of solution, bubbles are formed, and when the disturbance reaches down into the very bottom waters, the most gas-rich waters, that's when that tremendous fountain was produced, all that energy was produced. It didn't really happen like that. There wasn't a big bubble at the bottom and then came up to the top. That's sort of Hollywood. It's really hard to get that across to people to do the graphics right, but I think you get the point of the landslide triggering the gas burst. In fact, almost anything could have triggered the gas burst because when the lake becomes so saturated, close to saturation, it's essentially metastable. So anything that disrupts the water a little bit and moves it up a little bit could trigger a gas burst. All right, this is what then, so let me go back. So at this point, we knew pretty much what we needed to do in order to reduce the natural hazards posed by these lakes. We needed to put pipes down into the bottom of the lake, and we needed to degas the lakes in a controlled, safe manner. The problem was that the volcanologists still believed that this entire thing was caused by a volcanic event. And their scientific recommendation to the Cameroonian government was that, look, even if you could predict when a gas burst was going to happen, which you can't because we can't predict exactly when volcanoes are going to explode, there was nothing you could do about it. There would be nothing you could do about it. So there wasn't anything to do. On the other hand, our hypothesis said, no, you can actually go out and check all of the lakes in the country. You can see whether they have high concentrations of gas in the bottom waters, and if you find one that is dangerous, you can insert pipes and siphon off the gas slowly and in a controlled manner. Well, faced with the prospect of doing nothing, which was one of the scientific pieces of advice the government was getting, versus doing something about it, which would cost money, not surprisingly, the Cameroonian government decided to let the scientists battle it out and come to some consensus before they were willing to move forward. It took a couple of years, but what we started to find then were slow increases in gas pressure in the bottom of Lake Nyos. The gas was starting to build up again over time, just like our model had predicted. And at that point, the evidence became really overwhelming that this wasn't a volcanic explosion, the lakes were priming themselves to erupt again, and something had to be done. So the government allowed us to move ahead with tests on installing pipes in the lake. The result of that is this, picture of the gas water fountain in Lake Nyos. The pipe there, the pipe here is only about 13 centimeters in diameter, so it's a very small pipe, but the water fountain is over 50 meters high. So the way it works is quite simple. You put a pipe, these are polyethylene pipes, see them down in the lower right corner there. You install the pipe down into the lake. Initially, you apply mechanical pump to start the water moving up in the pipe. At some point, the water from the bottom gets up in the pipe, and the gas pressure pushing out equals the hydrostatic pressure pushing down, and bubbles are formed. Once that two-phase system is established, the bubbles start rising very buoyantly, and they entrain water, pull water up from beneath. So that in the end, the fountain runs itself. You don't need any more energy to run it. So the expansion force of CO2 is actually quite high. It's not as high as dynamite, but it's high enough so that at the surface here, the exit velocities in this very small pipe are near supersonic speeds of this gas-water mixture. You could connect a turbine to the surface and generate megawatts of energy, but the problem with that is that there are no power transmission lines in this part of the country. So, you know, I suppose you could rig up some giant carbon lights around the lake so you could see it from space, but that's really not going to do anybody any good. So this is the system that has been installed, one pipe in Lake Nyos and multiple pipes in Lake Manoon. And it's been very effective, at least in Lake Manoon, the smaller lake, in reducing the gas concentrations. So this is a picture of, again, the gas pressure with depth over time in Lake Manoon. Here you can see in 1992, the gas pressure at the bottom, these black circles, increased over time in 1998, increased in time again to 2003. Now in 2003, right at this knee in the curve, the lake was 97% saturated, very close to the hydrostatic pressure line. Just a little bit more gas or some disturbance in the lake and we would have had another eruption. Fortunately, that's just when we put the first pipe in. And almost immediately, that first pipe had a very positive influence in that it reduced the gas concentrations so that it moved it away, the pressures away from this hydrostatic pressure line and made the lake safe. This continued on, and by 2006, the gas had been withdrawn much more, lowered much more. And a couple of things to notice. One, this is the depth of the pipe inlet. So the gas pressures are still high down here at the bottom simply because the pipe can't reach them. After this, more pipes were installed and reached all the way down to the bottom. But the other thing to notice is that the structure of the system, the layering in the lake, has remained stable. So one thing we don't want to do is to destroy the stratification in the lake and cause another gas burst. This isn't the case at the moment now, Lake Manoon is completely degassed. This isn't the case in Nyos, though. It's much bigger. It has much more gas in it. There was only one pipe in it, and so we needed to know how long it would take. We needed to have some sort of a model to predict the future status of the gas. So we knew what the natural recharge rates were into the lake. And this is how we developed our model. We knew what was being pumped out by the pipe. We also knew how much was diffusing from the high CO2 bottom waters into the lower CO2 surface waters and then ventilating up to the atmosphere. And we could put all that together and run that model through time, and this is what we found. So this is now the gas content of the lake through time, and you can see that with one pipe, the black circles there, the lake is only slowly degassed over time. And in fact, the further you go through time, the less effective the degassing becomes, because the strength of the degassing is run by the pressure of gas at the bottom. The more pressure there is at the bottom, the faster the gas goes up through the pipe. So if you reduce the bottom water gas concentrations or pressures, you reduce the degassing efficiency. What we see here is that if instead you install 5 pipes, then you reduce the gas concentration much more quickly. And that process has now been, a couple of years ago, the UNEP and the European Union provided some money for a group to put some more pipes in Lake Nyos, and this is being done right now. However, this isn't the only problem at Lake Nyos. In addition to the gas problem, there's also a great flood danger in the lake. So this is the natural spillway that we saw initially here, holding back the upper 40 meters of the lake. And it's very weak and eroding rapidly. When it fails, it will produce a flood that could affect 10,000 people in the floodplain below the lake and reach all the way into Nigeria. So here's just a cross-section of this dam. The dam was in place when the lake was formed. It's composed of loosely consolidated volcanic pyroclastics that were laid down on top of this very hard quartz monzonite bedrock at the bottom. And the dam is already leaking. So it's leaking. The lake side is on the right, the stream side is on the left, and once the dam starts leaking, the experts say that they call that piping. Once a dam starts piping, it could fail at any time. They don't want to make bets after that. So we have a real problem here because we've got not only the gas danger, but we've got the danger from flooding. So what's our plan? Well, this is the remediation plan. Here, we pump bottom water out, we reduce the gas content. That reduces the danger of a gas burst. That's good. We've got 2 options now. We could lower the level of the lake, and that would eventually reduce the flood danger. So if we lowered the level 40 meters, that's how thick the dam is, deep the dam is, then we don't have that problem. But consider if we lowered the lake level quickly, we would essentially remove 40 meters worth of hydrostatic pressure from the gas that's still in the bottom water. We would depressurize the bottom waters and we'd have another eruption. Or if there are pockets of gas beneath the lake, we could depressurize them as well. So, on the other hand, what we're doing right now is keeping the lake level constant. The flood danger remains, but as we remove the gas, we reduce the danger that when we start lowering the lake, we'll trigger another gas burst. Once the lake gas content is low enough, then we can start reducing the low level of the lake and then go in and strengthen the dam or remove it. All right, that brings us to Lake Kivu then, the big nasty brother of Lake Nyos. It's 1,000 times has 1,000 times more CO2 in it. It's 1,600 times larger. It's got 35 million tons of methane in it as well. And with several million people living in the basin around the lake, this is the world's largest ticking time bomb. Kivu is different from Nyos and Manuna in another way as well. There are active volcanoes right around the lake which could serve to destabilize the water column, the stratification in the lake, and cause a gas burst. So here's a picture of an aerial view, satellite view of the Nyiragongo eruption in 2002. You can see the little red streaks of lava that went through the town of Goma on the shores of the lake. It destroyed about half the city. You can see the lava just flowing right through the streets there. The lava did reach the lake in 2002, but not enough of it went in to actually destabilize the stratification. So there was no gas release at that time. However, we also have the possibility that there is lava injected from beneath the lake in conduits from a magma body underneath the volcanoes rather than just coming in from the surface. And so here's this injection into the bottom of the lake, producing a tremendous amount of heat, lighter water that would then rise up and could destabilize the lake. These eruptions won't stop. There was another one at Yamagiri in 2010, just at the time when I was there for a conference on the lake. That was sort of thrilling. And in the bottom of the lake, there are actually volcanic vents that have formed seamounts. You can see in the lower right here, they almost look like little volcanic cones. So there is the great possibility that there will be some sort of a injection of lava into this lake, magma into this lake that will destabilize the lake and trigger a gas burst. Well, what do we do about it? Unfortunately, it's really not possible to degas this lake with these small little pipes that we used in Nyos and Manu. It's just way too large of a lake, way too big of a problem. But it turns out that there is one potential way of solving the problem, and that is the fact that the methane in the lake is of such great quantity that it's economically exploitable. Now, here is the other problem in the lake. The methane concentrations have been increasing over time. So the methane has increased in the bottom waters by about 15% in the last 30 years. And if you project this out, this increase, if this stays the same through time, will reach the hydrostatic pressure line, the saturation, in about 100 years. So we need to remove some of this gas from the bottom waters, and the way to do it is to do it through exploiting the methane as a natural gas reserve. In fact, the methane in Kivu ranks the 5th largest of any country in the world, 55 cubic kilometers of methane. And you can see here in this figure that the high methane water comes very close to shore here because the lake drops off very steeply. It's a very steep-sided lake, which means you could have fairly easy access from shore to that methane. The idea is to put platforms out on the lake, have pipes that go down, lift up the water in the same way that it works in Lake Nyos, and then siphon off the methane, separate out the methane, and pump the methane to shore on a pipe where it's burned in electric power generating engines. There's enough methane in the lake to actually export power to many parts of East Africa, so much so that the World Bank and the IMF are reconsidering designing their hydroelectric projects for East Africa because of this potential power source. So this is the power plant, a pilot power plant that's now operating on Lake Kivu. These are pictures from about a year ago. The gas comes up, lake water comes up from about 300 meters depth in this pipe like that, not that exact pipe. It's about 3/4 of a meter wide. The gas comes up and then is fed here through this blue pipe, big blue pipe here, comes up, and it's fed into first a large pressure vessel in the structure. And this is a picture then of the pressure vessel. In this pressure vessel, you can control how much absolute pressure there is and use that to start separating the CO2 gas from the methane. The methane is about 30% of the gas. The CO2 is about 60% of the gas, with the rest being some sort of noxious mix of hydrogen sulfide and some other things from the bottom waters. The methane is much less soluble, 25 times less soluble than the CO2. So at any given pressure, more of the CO2 will stay in the water and more of the methane will go out of the water. So you can start separating the methane from the CO2 in that way. Once the gas is initially separated, then it's fed into this large scrubber, about 3 to 4 stories high. And this scrubber here has water flowing down in it at varying pressures, which scrubs out essentially the remaining CO2. The methane that's left is collected here at the top of the plant and put together to be distributed to shore in this pipe. So here you can see it's actually a relatively small pipe moving this methane. It's about 1.5 kilometers to shore here. So it's not very far. Once on shore, that methane, the natural gas, comes in and is burned in these electric generators. Right now, this power plant is designed to produce about 5 megawatts of energy. It's producing about 3 megawatts now, so it's not quite up to full capacity. This is just a pilot plant. The first full-scale plant will produce about 35 megawatts of energy, which will double, one single plant will double the current energy output for all of Rwanda. So Lake Kivu is on the split between Rwanda on the one side and Democratic Republic of the Congo on the other. The power will also be 5 times cheaper than it is right now. They're paying about 25 cents per kilowatt hour for diesel generated power now in Rwanda, and this would be about 5 cents per kilowatt. So there would be plenty of power to export to other areas, and in fact, this methane store in the lake could actually become the salvation for this developing and relatively power-hungry part of the world. In addition, the removal of the methane gas is going to reduce the danger from a gas burst. So what this shows is the amount of gas in the lake over time with different numbers of these large power plants. So here's no power plant at all. The gas content increases. We plotted things out to about 2,200, so a couple hundred years. This is with 1 power plant operating. Here is with 3 power plants operating, and here with 6. Now, right away you can see that this has the possibility of managing this resource so that you don't pump it all out, but you actually have sustained power production over very long periods of time. The idea would be to reduce the gas content enough so that it reduces the danger of a gas burst for the people living around the lake, but still maintain enough gas in the lake, and the natural recharge of the gas will provide power over longer periods of time. Okay, what I want to do for the rest of the time is talk about some of the scientific spin-offs that these lakes have really catalyzed in our understanding of natural systems. In 1996, Joshua Zhang, who's a member of our geology department here, showed that you could model the gas-water eruption out of Lake Nyos similarly to a gassy eruption of magma coming up through a volcanic conduit. Essentially, the water itself acts as the hard rock does in a volcano to constrain the magma, and in this case, to constrain the gas water coming up to the surface. And that these gas-water fountains could be produced in water bodies of any size, including the oceans. Well, that insight of Joshua's then triggered a whole series of hypotheses about very large gas bursts that could have occurred in the past in the oceans that would have caused, for example, the Permian mass extinctions or the Paleocene-Eocene thermal maximum, times in the past when there were very rapid climate changes. Both of those ideas depend on the idea of methane clathrates. So essentially these ice-water mixtures that are frozen but that have methane or CO2 embedded within the structure, accumulating in subsurface, either in the water column or most likely in the sediments beneath the water, to very large concentrations, and then being released up to the atmosphere with some sort of a disturbance. For the mass extinctions, the idea is that this methane coming out would then be ignited naturally by lightning and would envelop a large part of the Earth, at least continental size areas of the Earth. That's what's required in order to explain something like the Permian mass extinction. So Permian mass extinction 251 million years ago, largest, the granddaddy of all mass extinctions we know about on Earth. 96% of all marine species went extinct. 70% of terrestrial vertebrates went extinct. It's the only mass extinction we know about where insects actually went extinct. It was a large one. It turns out that the paleoclimatological records show that there was an excursion in the 13C content, so the carbon-13 of the sediments during this time. And that is very consistent with the fact that methane has a very low 13C content. So that's just one of the stable isotopes of carbon. Its ratio changes over time and can be used as an indicator of past conditions. Methane has a very low amount of 13C in it, and during this time period and during the thermal maximum at the start of the Eocene, there were very low 13C contents in the sediment records throughout the world. In addition, there's evidence that there were paleobasins in the ocean that could have been of sufficient size to generate large amounts and contain large amounts of methane. For example, a basin in the ocean the size of the Black Sea today could hold about 10 to the 18th grams of methane, which is enough to essentially completely envelop the Earth. So there are the possibilities of these things, and this is really there's the methane fireball, well, an artist's depiction of the methane fireball that would have been required here. But a simple diagram or picture of how this would happen is shown here. Essentially, you have these large basins that go anoxic, no water in them. A lot of methane is produced. And then something like the slump or a turbidite or a landslide, subterranean landslide, like occurred at Lake Nyos, is produced here, which releases the gas and it goes up to the surface. Now, in the ocean, the water is so deep that the dynamics of the bubble itself rising to the surface become very important. And whether the gas actually diffuses into the surrounding fluid and the bubble shrinks as it rises, or whether the bubble is rising so fast that it expands faster than it can diffuse its gas into the surrounding fluid. Because the bubble is pure gas, and the surrounding fluid has very little gas, so it's going to want to go out. Whether the bubble makes it to the surface or not has a real impact on what kind of a gas burst you might trigger in the ocean. So given that as background, some recent work has produced a new model that looks at these dynamics of bubble growth or dissolution in relationship to these kinds of problems. And this is just a graph from this publication showing how over time the radius of the bubble in this situation is getting smaller. So the bubble is rising, but it's actually dissolving, getting smaller and smaller, may not make it up to the surface. Information like this is also critical for evaluating another idea that has recently become very important, and that's the idea of tackling our problem of greenhouse gas accumulation in the atmosphere by taking those gases and storing them in the deep ocean as CO2, liquid CO2 or CO2 clathrates or hydrates, these kinds of frozen CO2. So here the issue really is what happens to this hydrate shelled CO2 droplet as it moves up in the water column. So here we can see that Starting out at 600-meter depth, the bubble is about 5 millimeters. It rises over time, getting smaller and smaller to 400-meter depth. But at that point, the pressure of the water, of the weight on the water on top of it, is not enough to keep the bubble or the droplet from forming gas. Once it forms gas, it goes very quickly up to the surface and could trigger a bubble eruption. So these are the kinds of things that people are thinking about now based on what we learned from Nyos and Methane. Now, this theoretical model, this is still a theoretical model. There are lots of pieces of it that we don't really understand or can't model yet, but it can be applied to much more, well, sort of local or everyday phenomenon as well. For example, I'm sure that most of you have a general feeling of the difference in plume height that you get when you shake a bottle of Guinness versus Budweiser versus champagne. It's got to be cheap champagne, though. Expensive champagne actually has lower gas pressures than cheap champagne does. But it's always nice to have, to base that, to back up that empirical sense that you have with a theoretical model. That's what scientists do. So I'm sure that the kinds of developments in our science that we wouldn't have thought about or wouldn't have understood because of these really fascinating lakes, these gas-charged lakes that I've been talking about, will continue in the future as we learn more and more about them. So what I want to do at the end, in summary, is just give you a little list of some of the things that I have found are very important in dealing with scientific debates. And this can apply to natural hazards or to climate change. You know, in many natural hazards, there really isn't much of a debate because there's nothing you can do about it. You can't stop a tidal wave. You can't stop a volcano. But these are natural hazards where you actually can go in and mitigate the hazard before something bad happens, which is why the Office of Foreign Disaster Assistance funded this, because we were able to show that we could stop a disaster before it happened, and that was worth doing, rather than going in afterwards and just picking up the pieces. So the first thing, the scientists in the audience may say, well, of course, this is what you do. But it's surprising how many people sort of forget this. First, of course, is doing good science. Second is understanding the alternate theories. It wasn't until we really understood what the volcanologists were telling us that we were able to show and convince people that it wasn't happening in that way. Despite what you might think of, given the politics that surround us today, logic does defeat hand-waving in the end. And if you explain principles to politicians, the solutions will become self-evident. With the caveat that I have down there, unless they stand to make money from one of the solutions, and that's a big problem. I want to end just by saying that I never considered myself that well equipped or just right to do this kind of project. I think the results are much more a function of picking a problem and sticking with it for 20 years. In my mind, science and scientists are being marginalized in our society. And I base that on at least 3 pieces of evidence. The first is that most people in the world don't understand the difference between ozone and greenhouse gases, let alone the ideas of ice ages or climate change or even ocean circulation. Second, by every measure that we have, American school children are losing ground in terms of their skills in science, math and science, relative to the rest of the world. And third, our great ambassadors of science, Carl Sagan, Jacques Cousteau, have been dead and gone now for decades, and they haven't been replaced. Science and environmental problems are at a real crossroads right now. And my message to the younger scientists in the audience is that although the pressures to go out and publish in a science journal are very great, And if you take the time to try to show how your work fits in a more applied area, why it's important that we do basic science, you'll publish fewer of those articles in science journals. In the end, I think, who cares? Because you'll publish 2 or 3 fewer papers over your career and it won't matter. But the chance that you pick a problem now and stick with it for 20 years, something that's important to you, could have very great benefits in increasing the stature and the understanding of science that we have in our culture today. So with that, I want to thank you all for coming. Thanks a lot for listening to me. And I think I'll take questions after a break.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.